Jnanam paramam dhyeyam. Knowledge is supreme.
Okay, welcome back. So, we'll try to finish this first module on process dynamics, where we try to understand how a process responds to changes in inputs by looking at how can we predict the response of any transfer function given there is some step in the input. So, we will try to see, or I will try to give you some tools in terms of predicting the response of any transfer function, and this we will be doing by finding out poles and zeros of that transfer function. So, what we need is the transfer function. Once we have the transfer function, we should be able to predict its step response by using these steps. So, the first step, let us say this is for a transfer function of the form ns over ds. So, the first step is to find all the poles and zeros, and the next step is you use the final value theorem, and in certain cases initial value theorem as well. And with the help of these two, we would be able to predict response, step response of any transfer function. So, for that what we do is we try to plot these poles and zeros into the complex plane. So, this is the real axis, this is the imaginary axis, and in this figure for any transfer function we will plot or we will put the poles as well as zeros. So, we will start with poles. So, let us say the pole of the system falls at the origin. So, this is our origin. Let us say if the pole is at the origin. So, when the pole of a system or a transfer function is at origin, the denominator of the transfer function will have a term 1 over s, or the denominator will have a term s. So, when we have a step response, it will be get multiplied by 1 over s. So, we will have terms like s square when we look at the transfer Laplace of ys. So, in such a case, when you have pole at origin, the transfer function will have s in the denominator. So, when we talk about ys, it will have s square multiplied by something. So, when we want to take ys in terms of partial fractions, in that case we will be writing it as a over s plus b over s square and the other terms. So, what we are going to have is b over s square, the inverse of that will give you bt. So, even though so this system will increase linearly with time, or the one of the dynamic modes of this system will increase linearly with time. So, whenever you have pole at origin, it will be an unstable system. Or grows linearly with time. So, it will not have a stable final value. So, that is the case when you have pole at the origin. When we have pole on the real axis, any pole on this real axis in the left half plane, so with a negative value, what we are going to have is the response will have e raised to minus some lambda t terms, which all will decay down to 0. So, all these will give you stable response, to stable or finite response, overdamped response. there will be no oscillations in such a case. The oscillations will come if the poles or there are complex conjugate poles. So, if you have any pole in this quadrant or this quadrant, again still in left half plane, what you will get are decaying oscillations. These terms will give you e raised to power a plus bi. So, there will be e raised to at and e raised to bit. So, that first term will give you the magnitude of oscillation and the second term will give you sines and cosines. So, as the magnitude is on the negative side, the oscillations will decay, but there will be oscillations when you have the poles on the left half plane, but not on the axis or the real axis. Exactly opposite case would be when we talk about the right half plane. So, this is the case when all the poles are on the left half plane. Now, if any pole is on the right half plane, if it is on the axis, it will be e raised to power some positive number times t. So, the response will just grow in time. So, the response will be infinite when time goes to infinity. So, all these would give you unstable or infinite response. This happens when any of the pole is on this side. Even though n minus 1 poles are on the left half plane, even a single pole on the right half plane will give you these kind of responses, because all these will die down to 0 as time t goes to infinity. So, the only thing which does not die down to 0 will be anything on the right half plane. Similarly, if we have some complex conjugate poles, these will give you oscillations, but these will be growing oscillations. So, the oscillation magnitude will keep on growing as a function of time, and again you will get infinite response as time t goes to infinity. So, if any pole or any pair of poles is on the right half plane, you will have such infinite or growing responses. The last case which is remaining in this is if your poles are complex conjugate, but or with real part which is 0 or purely imaginary poles. So, in that case what you will get are sustained oscillations. Which is also known as marginally stable process. So, depending on where your poles of the process lie, you may have an overdamped response, stable and finite, you may have decaying oscillations, you may have growing oscillations, you may have an unstable or infinite response, or you may have sustained oscillations into your system, and lastly you may have an integrator which increases linearly as a function of time. So, depending on the values of poles for a system, the overall dynamic modes of the process can be calculated by simply looking at the poles. Then next comes are the zeros. If I want to summarize this, what you would get is, so pole at origin gives you integrator, pole real and negative will give you overdamped response, complex with negative real part will give you decaying oscillation, and then the opposite side of that would be real and positive, so infinite response, complex with positive real part will give you growing oscillation, and then purely imaginary pole will give you sustained oscillation. So far we have not looked at where the zeros of the system are. So we will now see how this analysis changes when we have zeros into the system as well. So when you have 0 into the system or 0 at origin, the transfer function will be of the form s in the numerator. So whenever you try to find out the final value, by the final value theorem, it will be limit s tending to 0 s of ys is equal to limit s tending to 0 s times the step response. So it will be limit s tending to 0 a times g of s, and as 0 is at origin, g of 0 is 0. So the final value of the response will be 0. So whenever there is a 0 at origin, the response decays to 0. So the final value of the output will always be equal to 0 whenever there is a 0 at the origin. So if we go back to this figure, so if I say there is a 0 at origin, then it will give me response goes to 0. Now for most of the parts, 0 would just change the relative contribution, which would not be directly predictable. The only case when you can predict the response of a 0, so let us try to use a different figure for 0. So this is real part, this is imaginary part. So if there was a 0 at the origin, the response decays to 0. Now if the 0 is on the real negative real axis and it is closer than any of the poles, so this 0 is on the real negative real axis and it is closer than any of the poles to the origin, in that case you will get overshoot without oscillations obviously. So this was the case when we had overshoot into that first order or second order system. This is the type of 0 which is closer to origin than any of the poles. Those cases will give you overshoot. And the other case which is going to give you interesting results is if the 0 is on the right half plane. So if the 0 is a real 0 on a right half plane, it is going to give you inverse response. So by putting the 0 also into the complex plane, you can predict whether there will be an overshoot without oscillation or whether there will be an inverse response. This will be on top of the way we predicted the response for the poles, and the combined response will be the combination of these two factors. And then lastly, something which you should also keep in mind while predicting the response is the initial slope of response. So that is dy by dt at t equal to 0. So that depends on the difference, write it the other way around, degree of the denominator polynomial minus the degree of the numerator polynomial. If this difference is greater than 1, then the initial slope will be equal to 0. That was the case when we had a pure second order or a pure higher order system. In that case, the denominator polynomial degree was greater than the numerator by 1, more than 1. So, in that case, the response does not start immediately. The response has a 0 slope at time t equal to 0. When the difference is equal to 1, then the slope is finite. The slope is not equal to 0. The response immediately starts. And if this difference is equal to 0, in that case dy by dt is not defined and there is a discontinuity in y. So, this was the case when we have the lead lag type of dynamics. This was the case of the first order dynamics, and this is the case when you have second or higher order dynamics. So, by knowing the initial slope or how the response starts, then looking at whether you have overshoot or inverse response, and then also combining it with whether you have stable response, overdamped response, growing, decaying oscillations, growing oscillations, all that in combination you would be able to predict response of any transfer function for a step change. So, to summarize, what we have seen is the poles of the system or transfer function will give you what are the dominant modes of that particular dynamic transfer function. The zeros will give you the relative contribution and will also give you some conditions when you can get overshoot or inverse response, and then these values of poles and zeros will help you to predict response of any dynamical system. So, at this point we have finished analyzing how dynamical systems behave. So, in the context of this course on process control, what we have seen is given a change in the input, how the system responds. So, now we have a better understanding of the process. Once we are now at a position that we know how the system is going to behave. So, now we can have a way to control the process. Now we are at the stage where we know how the system behaves. So, we know exactly how in order to move the process from one point to the other, how we should change the input of the process. So, it is more like solving an inverse problem. So, as we know the way process behaves, we should be able to now tame its behavior or make the process behave the way we want. So, that will be the part we will be discussing under the second module of this course, which will be on process control. So, thank you.